The next topic we're going to cover deals with Java barrier synchronizations. And as we'll see, there are a number of different ways in Java to do barrier synchronization. We're going to focus primarily on CountDownLatch, CyclicBarrier, and something newer in Java 7 and 8 called the phaser, which is kind of cool. And we'll talk about the different mechanisms and how they work, and we'll compare and contrast them and so on. But first, let's talk a little bit about barrier synchronization. And that's why I had you watch that movie clip from Miracle. And we'll talk about that in a second. So first of all, what is barrier synchronization? A barrier is a synchronization method or mechanism that halts the progress of one or more threads at a particular point. And if you go here, you can read more about barriers. There are barriers that occur in computer science at different levels. There's really low-level hardware barriers, and then there are higher-level things. These are the ones we're going to be focusing on primarily. Of course, there's also a pile of cool human known use barrier examples. Here is one barrier example. This is a one-shot barrier example. So all the horses have to line up in the starting gate, and then once they're all lined up, they hit the button or whatever, they shoot the starter pistol, and then they all start to run. And as you'll see, there's a couple of different ways to use barriers. One way to use them is in terms of the number of iterations that they run. For example, some barriers, like the horse example, is an example of a one-shot barrier. You do it one time, everything starts in motion, and then when they finish, they're all done, and they don't line up again and start over right away. Other things have a cyclic model to them. So they do a phase of stuff, and when they stop, then they all kind of get back in line, and then they start over again. That's a cyclic barrier. Can anyone think of an example of a cyclic barrier?
Wind sprints.
Wind sprints, right, exactly. So that's the part I didn't really play you from the classic clip from the Miracle movie, but you know, if you watch 5 minutes of the clip, he has them doing wind sprints over and over and over again, trying to get them to say that they play for the US, not for their high school team or their college team or whatever it was that they kept saying over and over again. So that's a cyclic barrier, right? You redo it. There's other examples we'll see in a second. There's a couple of other dimensions, whether you have fixed number of parties or a variable number of parties. Parties are the participants in the barrier abstraction. And so many barrier models have a fixed number. You start out with n, and even if you iterate over and over again, you still have n every time. And if you have more or less than n, it doesn't work at all. There's another model that has a variable number of parties. And this is how these things map to Java classes. So the CountDownLatch basically gives you one shot with fixed number of parties. CyclicBarrier gives you CyclicBarrier with a fixed number of parties. And then there's this thing called a phaser, which gives you either one shot or cyclic with a dynamic number. You can also do it for a fixed number, of course, too. The thing to keep in mind also is that you can use these barriers to have many threads wait for one thread, or one thread wait for many threads. And we'll talk about a whole pile of examples here in a minute. All right, so let's start by talking about some examples of how this stuff works. Let's assume, for sake of argument, that we've got some kind of program where it makes sense for a group of threads, a gang of threads, if you will, to all run in parallel on different data sets doing the same computation. So here's a simple example. You might have a video rendering program that will go ahead and take a number of videos and do some video conversion on them. And you could have the program all running, you know, with as many cores as you're willing to devote to the problem. They could all run in parallel if you wanted to, because they're all doing the same thing. So one way to use a barrier is something called deferred start. And in deferred start, you have a main thread that typically will kick off a CountDownLatch or phaser can be used for this. You'll have a main thread that spawns a number of worker threads, and while those worker threads are busy starting up, the main thread goes off and does some time-consuming initialization. It maybe balances a database or it initializes a database. I'll show you an example from Android here shortly. So it goes off and it does a bunch of stuff. And meanwhile, these other threads, once they're up and running or once they're started, they need to wait until the main thread is done with its initialization before they can start. So in this model, it's a deferred start barrier. The main thread is deferring the start of these threads. And once the main thread is done with whatever initialization it has to do, it sets the count to 0, and all these threads can go ahead and start to run. Can anyone think of an example from, from everyday life or just from a human known use that uses deferred start? So, yeah, Jonathan.
If you pass out tests and you say no, everybody wait to flip it over or whatever.
Yeah, that's a good one. Or the other example might be the horse race thing. You get everybody sort of lined up, and maybe you're off checking something or other. Or at the Olympic events when they do downhill skiing, they get everybody into the gates, and then they wait till they're all ready. Or maybe swimming, when they do the starter pistol. Those kind of things where a bunch of threads all start at the same time, but they all have to wait until the coordinator is ready. A symphony orchestra maybe is a good example too, right? The next approach, another form of a barrier, is called await done or await completion. And the idea here is that you block until all concurrent threads are done with their processing before continuing on, before the one thread continues on. So a countdown latch or a cyclic barrier could be used for this. So here we have a model where the main thread of control, maybe after it kicks off all the worker threads, it's now going to wait for them all to finish. And once they're done, as they complete, then finally when they're all done, the main thread can continue on its way. Can anybody think of an example from everyday life that works that way, where one thread waits for others?
If you're proctoring a test, you can't wait until you get them all back.
There you go. That's a great example. Another similar one would be like shutting down if you work at a store or something like that, you have to wait till all the customers leave before you can shut it down. So yeah, good example. So both of these approaches are typically one-shot kinds of things, or could be used in a one-shot way. The next model is cyclic processing, where either a fixed or a variable size pool of threads run concurrently, and they all wait for each other to reach a common barrier point before repeating the cycle again. So we might have, in this case, we could have a cyclic barrier with a fixed size number of parties, or a phaser with a variable size number of parties can be used here, where these cycles occur. And as we talked about, the example with the wind sprints or something like that. And I guess with the wind sprints example where teammates pass out, and they have to be taken to the hospital, right? So okay, those 5 guys, they just collapsed from exhaustion. Take them off. Let's keep going, right? So that would be a model where you'd have a smaller number of participants as you continued, or maybe some other people, were late to practice, so they get there late and they have to run wind sprints again. Who knows? Those are examples. All right, here's a human known use that I think is actually pretty good that works for all these things. A museum tour guide. You guys gave other good examples too, but this is one I'd come up with. So hopefully you know what a tour guide is. Deferred start. So a bunch of tourists come to the museum and they all have to queue up waiting for the museum to open. Once they're in, as the museum closes, the people who work in the museum can't leave until the last group of tourists all leave. And then cyclic processing, you might have a model where the docent or the museum tour guide or whatever takes people from exhibit to exhibit or room to room. And they take them there and they give them all an overview, and then they say, okay, now you guys can wander around for a while, 5 minutes or whatever, and look at the different paintings or sculptures or whatnot. And then when everybody comes back, we'll then collect the group and we'll move on to the next thing. Right? So that would be sort of cyclic. You go from room to room. And you could use this for both fixed or variable size number of tourists. You also do similar things like on field trips. When you were a little kid, you go on a field trip and you're not supposed to leave till you get everybody accounted for, right? Because that would be bad. All right, so that's kind of the background of barriers. To make this a lot more concrete, we're now going to take a look at a little framework called the ThreadGang framework. And we're going to use this to motivate and then ultimately look at a bunch of code examples for all of these different kinds of frameworks. So here's what the ThreadGang framework looks like in its full-blown glory. You can actually go to GitHub and take a look at the code. It's all right there. It's still evolving, but it's basically what I'm showing you here. So here's the thing called a ThreadGang. We're going to look at that first. And then we're going to look at the instantiation of the ThreadGang framework with all kinds of different barrier mechanisms. And we'll talk about what problems they solve, and then we'll look at the code, and you'll see how it all works. So the ThreadGang framework is intended to work for groups of threads that can currently process input from a generic vector of elements E for one or more cycles. So the basic idea here is we want to be able to use this for so-called embarrassingly parallel computations, things where there's little or no dependency between the problem pieces. So everything can kind of run in parallel. Washing your clothes, lots of loads of laundry, that's embarrassingly parallel. You don't have to stop and, the sock in one washer doesn't have to wait for the shirt in the other washer, right? They just all run in parallel. As many washers as you can throw at the problem, you can all run them together. We're also going to use this as a way to analyze commonality and variability analysis as it pertains to frameworks. I probably mentioned this a couple of times. Frameworks come from conducting commonality and variability analysis in a domain. And the goal is to figure out what things are common, which become the classes and or methods, often abstract methods, in base classes. That's the fixed part. And sometimes there's actually common algorithms using patterns like template method or strategy. Those are fixed. And then a lot of other things can vary based on certain aspects of the domain that will be different over time for different uses. So we're going to see a really cool example of this. And the point here is, some things are the same, some things are different. So here are some of the things that you, the user of the ThreadGang framework, need to customize in order to be able to use it effectively. So these are all things in the domain that can vary. So one thing that varies is, where does the data come from? Does the data come from a file? Does it come from a string? Where does it come from? Does it come from a network connection? The data can come from all kinds of different places. And so we're not going to presuppose where the data comes from. All we know is that it came from somewhere. It's not our problem where it came from. And we're going to get it delivered to us as a vector of elements. So as long as you can give this thing as a vector, then it can be whatever you want it to be. So vector, get vector, and set vector are ways you can parameterize. Subclasses can parameterize this to set its input. Another thing is, how many cycles does it run? Does it run one time? Is it a one-shot gang? Or is it a cyclic gang? And there's a couple things in here that are going to be used to influence this. So there's a method called getNextInput, which gives you back a new vector. And if you're done, then it gives you back null, which means there's no more input. So that's the end of the thing. And that might take place the first time, or it might take place the nth time. Depends on whether it's a one-shot or a cyclic framework instantiation. Run next cycle is going to be used by the threads to determine what they should do at the end of a cycle, whether they should block or wait or do whatever they need to do. Another thing that the framework allows us to do is to customize the structure of the concurrency model and the barrier synchronization model. So you'll see there's several different ways of doing barrier synchronization. We'll talk about using joins, thread joins. That's a really basic barrier synchronization model that's supported by Java. We're going to see CountDownLatches, which are a little bit more sophisticated. We'll see the use of CyclicBarriers, which are yet more sophisticated because they support cycles or iterations. And then we'll see the last and final one, which is phasers, which are really off the deep end in terms of their coolness, but also their complexity. And so some things that you do here, you can determine how these things work and what mechanisms get used by the subclass. And then you can also influence whether or not you spawn threads or use an executor. And we'll talk more about executors later. Spawning threads is the most obvious way, but you could end up with a lot of threads. So executors are also useful. And then these are the different kinds of barriers you can use. Another thing to do is, what type of processing do you want to have done, which you have to specify. Obviously, the framework doesn't know what you want to do with the data that you give it. And how to process the results. When you're done processing the data, you need to do something with the results. How you do something with the results, again, is something that you have to tell the framework. It knows there will be results to process, but it doesn't know how to process them. So these are some more things that you have to do as the user of the framework. You have to figure this out. And whether this is done synchronously or asynchronously or whatnot, that's what you have to decide. And then finally, is this finally? Yes. Finally, how do you wait for the gang to complete? So there are various ways for the main thread of control to wait for all the other threads that it set in motion to finish up. And so you can decide. Common things would be to use thread join or countdown latches or something like that. OK. So that's the variability stuff. That's done by subclassing. And when you subclass, you override one or more of these methods and customize them for whatever it is you need to do to give you that behavior that your particular instantiation needs. And you can see that there's a whole bunch of things. So that's a framework. Any questions about the framework part of this? OK. The framework itself supports a bunch of commonality. Obviously, there are all these common method signatures. So each of these things has been thoughtfully put in there for a reason. They do something that are needed. And they can then be customized, but the customization takes place in the context of the common framework methods. So that's one form of commonality. Another form of commonality is common algorithms. For example, you'll see that there's a method called run, which is really the thing that drives the whole gang. And what run does is it gets the next input, so it has something to work on, and makes the vector whatever the input is, initiates a thread gang, typically a thread for every element in the vector, and then it goes ahead and waits for the whole thing to be done. And then, of course, in the meantime, all these guys start running in background threads, and they do the processing. And we'll talk more about other stuff. There's some other methods here, like, which one is it? The make worker method also does some cool stuff on your behalf as well. So you don't have to write these algorithms yourself. They're done for you. Now, quick patterns question. What pattern is this? Template method, exactly. So we have a fixed set of steps in an algorithm, and we allow the subclasses to vary what these things do. So you'll see how the whole thing kind of plays together. OK, so before we go on to look at the discussion about the concrete mechanisms, let's just pop over here real quick, and we will go take a look at the implementation. If I can remember where I put it. Dropbox, Documents, Vandy, CS282, CS282, EX, ThreadGang. All right, there's the ThreadGang. OK. And here is the ThreadGang itself. The ThreadGang is an abstract class which is parameterized by the type of element that we're going to process and the result value. And a ThreadGang implements runnable, so that means, of course, that it has a run method. It has a volatile vector. We'll see why it needs to be volatile later. That needs to be initialized by some factory method. We have the set vector and get vector methods that return the input. Here's the abstract method called getNextInput. Obviously, the framework doesn't know where the input comes from, but you do. The user of the framework does. But we know we need to get that input, so that's a factory method that's used to get the input when we need it. Here's the initiate ThreadGang method, which you give it a size of the number of threads you want in your gang. And you have to fill that in because you know how to do that. Here's the run next cycle method. By default, this returns false. You'll see where this is used in a minute, which means that by default, the ThreadGang framework supports a one-shot ThreadGang. If you want it to support something other than a one-shot ThreadGang, you need to go ahead and put in some kind of cyclic barrier to block this guy until everybody reaches the point where they can run. OK? Here's a wait ThreadGang done. That's a method that's used by the main thread to wait for the other threads to finish. Here's the worker done method. Worker done is the hook method that's called when a worker thread is done. That's where you decide whether you need to keep going or not. We'll take a look at that. There's also a method called do work in background, which is where it actually does the user-specific logic running in a background thread. It's given some data to work on from the vector of data. Process results is another abstract method that do work in background needs to call back on. Hook method that can be used by do work in background to process the results. And here's the run method. This is the guy that really does the main work. It gets the first chunk of input from whatever mechanism you define. It initiates the ThreadGang to make a number of threads that will be as big as the set of work to work on in parallel. And then while those guys are off and running, it just waits for everybody to finish. So we await the ThreadGang being done. And then the final method in here is something called makeWorker. And this is a helper method that you can call from your initiate ThreadGang method. And what this guy does is you give him it's given the index into the vector that this particular thread will process. So this is the index. If you have a vector with 4 items, 0, 1, 2, 3, 0, 1, 2, 3, this is the index for a particular element in the array. And when it's called, you make a new runnable. And this guy's run method in the runnable goes into a do-while loop. So that means that everybody executes at least once in the ThreadGang model. And what it does is it comes in and it grabs the index of the element from the vector. So now we've got our data to work on. So you have a vector, and we grab the indexed item of it. And we take that element and we go and do work in background. Remember, do work in background is the hook method that you define that does whatever you want it to do. So we do work in background. And then after we're done, the worker done method gets called. And worker done has to decide what to do, right? Will it wait on a barrier or not, right? If it's a cyclic ThreadGang, it'll have to wait on a barrier for everybody else to finish so everybody can do the next cycle together. If at any place along the line something's gone wrong, we get an index out of bounds exception, and then we kind of take ourselves, we stop running in the thread. Otherwise, we just keep looping. Oops, there's a while down here at the bottom. So we basically are going to keep running until the whole thing is instructed to stop, until there's like no more work to be done. So that's the basic loop. So this is part of the framework. You don't have to write this code. This code is given to you, and everything else then customizes from that. Now, we're not going to look at this at the moment. We'll come back in a minute and look at this. But here's how you actually use this stuff. So the ThreadGang test basically does all the different barrier synchronization mechanisms we're about to talk about. OK, so that's background on the framework. With that as background, now let's talk about the Java CountDownLatch. So the Java CountDownLatch is one of the more fundamental barrier synchronization mechanisms in Java. And basically what it allows you to do is it allows you to be able to use deferred start or await done barriers. Those are the things it works best on. And it's purely one shot. And you'll see why in a second. Unlike some of the other mechanisms we've looked at, like the reentrant lock, reentrant read-write lock, condition object, CountDownLatch does not implement an interface. It just has the code. It does, however, implement a variant of the bridge pattern. It's kind of a lobotomized bridge. It's sort of funny. So what it does is it has the CountDownLatch interface, which then delegates to an implementation, but there's only one branch of the implementation. There's not a variety of things. And the reason it does this is so it could reuse large chunks of abstract queued synchronizer. So here's what it looks like. There's a class called sync. Sync extends abstract queued synchronizer, so it gets a lot of its behavior from that. When you create a CountDownLatch, you give it the count. Now the count is a little bit like the semaphore. With a counting semaphore, you give a counting semaphore a count. Except the difference with this is with a counting semaphore, as long as that count is above 0, you can make progress, right? The semaphore can acquire the thread can acquire the semaphore and make progress. With a CountDownLatch, conversely, until the count hits 0, you can't make progress. So you have to block. Once you set the CountDownLatch's count, you cannot reset the count short of creating a new CountDownLatch. When we come a little bit later on and we talk about phasers and cyclic barriers, you'll see that they they give you some additional flexibility there. The key methods in CountDownLatch is actually a very, very simple class. There's not a lot going on there. There's await, two variants of await, and something called countdown. As you can see here, these implementations just forward to the underlying abstract queued synchronizer methods. Here's the await method. This is the one that blocks and does not have a timeout associated with it. Calling await causes the calling thread to wait until the latch's count reaches 0. So whatever it is at this point, if it's not 0, if it's greater than 0, we're going to block until it reaches 0. Conversely, for this await, this is the timed await, this guy will wait until the timeout elapses or it reaches 0. And finally, countdown goes ahead and decrements the count by 1. Naturally, once it hits 0, then everybody who's waiting will be wakened up or be awakened. However, if you call countdown, you're under no obligation whatsoever to have to wait until the count reaches 0. You're just like saying, OK, you guys go ahead and start. I'm going to go off and do my thing. You're not obliged to stick around and synchronize unless you want to. You can, but you don't need to. OK, so let's talk about an interesting example of CountDownLatch in the context of Android. This is kind of a fun example. So in your Android phone, if you have an Android phone, there's something called the ContactsProvider. And that's, not surprisingly, what stores all the information about your friends, right? And it's got it's a very complicated data structure. And a ContactsProvider ultimately inherits from something called a content provider. We'll be talking about content providers later in the course. A content provider basically is a way to access a database. And as you'll see later when we talk about this, it's got all the various CRUD methods, the ones like insert, query, update, delete, and so on. And under the hood, there's a bunch of database tables. Your contacts, various accounts, history of the calls you make, all the kind of stuff that are used by various applications like the phone app or the People Finder app, People app, whatever, to look up various things about your contacts. But there's a bunch of those tables. And initializing all those tables takes some time. So they do a really clever thing in the Android ContactsProvider implementation. They use these countdown latches to guard access to these tables. So you can only access these things once they've been initialized. And we'll see in a second how this works. This is a good example of deferred start. So here's how it works. If you look at the ContactsProvider implementation, its onCreate method calls something called initialize. And initialize goes ahead and creates something called a handler thread. We'll talk more about handler threads. For the time being, just think about a handler thread as a thread that runs in the background and does something. And it goes ahead and starts the handler thread. So now there's a thread that's running. And that background thread is doing a bunch of stuff. It's going to be doing the initialization of the ContactsProvider databases. Remember, there's multiple tables. And what happens here, I won't show you the implementation here, but there's a bunch of method calls called schedule background task. And these guys, there's 9 calls to these methods. And each of these calls takes a different portion of the overall set of tables in the ContactsProvider. And it creates a message, and it sticks it on a message queue. And that background thread sits there and reads those messages off one at a time and does the designated initialization in the background. So notice that the rule here is that the other methods that want to access the ContactsProvider are not allowed to access the contents until the initialization is done. Because obviously if you initialize this big giant database while it's still halfway initialized, you get weird results. So to do this, there's a pair of countdown latches, one for read access and one for write access. And here they are. They're initialized both to 1. And that means, remember, what does it mean if a countdown latch is equal to 1? You have to wait on it until it reaches 0, right? So what that means is when the initialize method returns before all the background processing is done. So that means that you created the content provider, but it does a lazy evaluation model. It returns very quickly, but the complete initialization of the database is not finished. So that means you're getting control back as a user before the initialization is finished up. So what they do to make this work is they split read and write access into two countdown latches in order to optimize performance. And the idea is that stuff that needs to read, let's assume that that initialization is done relatively quickly. So as soon as read initialization is done, any readers can go ahead and make queries. And as soon as anything that requires initialization for write operations is done, then you can go ahead and do the write operations. And the way this is enforced is that, say, here's the query method. When query gets called, it's actually going to end up calling this thing called wait for access. When insert gets called, it's going to end up calling this thing called wait for access. And we'll look at wait for access's implementation in a second. But notice that wait for access takes the appropriate latch, either the read access latch or the write access latch. And here's what it looks like. Wait for access will loop waiting for the latch to become 0, at which point it knows it now has read access or it has write access. So it blocks waiting. Now those perform background jobs we were looking at before, the ones that are set in motion by schedule background task. Here's what perform background task does. Background task, this is what's called in the background, as you might expect. And for each of the initialization operations, like open for read for write access, open for initialize, and so on, it goes ahead and it counts down on the appropriate latch, either the read latch or the write latch. And once this is called, then any blocking calls that are waiting to get access can go ahead and proceed. So this is a really cool example of deferred start. OK, so that's a industrial strength version. You can go look at Android and be marveled at all the cool complexity that they have lurking down in there. I'll also give you a much simpler example. This is the one that's using our ThreadGang framework. This is the search one-shot ThreadGang CountDownLatch class, which is part of it's nested in the ThreadGang test, and we'll look at this in a second. The way this works is this particular use, and we'll look at the code in a second, customizes the ThreadGang framework to spawn a thread for each element in a list of input strings. So we're going to have a bunch of elements. Imagine this is an array with a bunch of elements in it. And each element will be a string. Now, this string could correspond to a binary that you want to search for malware signatures. It might be an image that you want to render or process in some way. It might be, if you're the NSA, it could be a database of terrorist call logs, and you want to search them to see who's calling, Osama bin Laden. Well, he's not going to pick up that phone, I'll tell you that. But you get the point. You're looking for stuff. And what happens here is each thread in this array runs the same logic. And here's what it looks like. This is the work that's done in the background. For every search string we want to find, so we have an array of words to find, it's going to go ahead and it's going to look up in the input data, which could be this giant array or this giant string with lots and lots of data in it. It's going to go and look up in there and try to find it. And if it finds it, it's going to go ahead and stick it in this process results method. And who knows what's going to happen there. It's up to the implementation. We'll see that in a second. OK, so let's go take a look at the code. And this will illustrate how to use a countdown latch. So we're going to look for CountDownLatch. And here's CountDownLatch. So the first thing to note is that search one-shot ThreadGang CountDownLatch, which is a bit of a mouthful, inherits from a class called search ThreadGang common. So let's go look at that guy first. So search ThreadGang common is a helper class that factors out a lot of common code. The search ThreadGang common class is abstract, which means we have to customize it yet again. We have to subclass from it. And it extends the ThreadGang framework with a string to search and a string as the result. We could change that, of course, but that's what we're doing here. It has an array of words to find, a count of the number of arrays of strings to search. This is basically keeping track of whether we're iterative or a one-shot thing. This is a one-shot thing. Here's the factory method that returns the next chunk of input. The first time it's called, it'll go ahead and return the input string as a vector. Here's what the input string looks like for the one-shot strings. I will come back and explain what they mean in a second. If you're really a musician, you can probably spot it already. So that's how we get the next input. Now keep in mind, this could have come from a file. It could come from a network. I just stored it in an array to make it easy. So that's the reusable code. And process results just goes ahead and prints it out. Here is do in background. This is what we just looked at a second ago. So this goes through every string in our array of strings. And for every string in every word in our array of words, it goes ahead and goes and looks up in the input to see if we find it and how many times it does, and it keeps track of if it's found or not. OK, so here then is the CountDownLatch version. And you can see it has a countdown latch called mBarrier. And here is the constructor, which just calls up the superclass. Here is initiate ThreadGang. And so what initiate ThreadGang does, this is the guy that's called from internally to the framework. So if you recall the ThreadGang file, in the run method, which is the thing that sets the whole framework in motion, initiate ThreadGang is what gets called after we've got our chunk of input, and its purpose is to spawn off any threads that we need to have. So here's initiate ThreadGang. We go ahead and make a countdown latch with an initial count of the number of elements in the vector, because this is going to be used to basically as an await done barrier. So we create the barrier to await all these threads to be finished processing. And then we iterate through from 0 while 0 less than size, and we go ahead and we make a new thread that's going to have a runnable returned from make worker for that location in the vector. And we're going to go ahead and start that thread. So after this line of code gets run, we've got n threads or size threads, all of which are running a runnable return from make worker. And if you go back over here and you look at make worker just creates a runnable. And what the runnable does is it keeps running while we're not done. This is a one-shot thing, so it only runs once. It grabs the data from the vector, runs the work in the background, and then calls this hook method called workerDone. We'll look at it in a second. So that's basically the life in a one-shot ThreadGang using CountDownLatch to serialize or to synchronize on the completion of the tasks. And then here is workerDone. The workerDone method, as you can see here, is called whenever we're done processing in the background, workerDone is called back from the framework, and workerDone decrements the count by 1. So it counts down the barrier by 1. And await ThreadGang done is what the main thread calls. So the main thread that started this whole thing off, after it initiates the ThreadGang, it calls await ThreadGang done. It just blocks awaiting the count to drop to 0. So that's basically the implementation. And I'll pop back over and just show you the picture again here. So what we have is we've got, let's say we have 4 threads just to make it concrete and match the slide. So we have a vector of 4 items. Each item has strings to process, and each item has a thread that's processing that item's strings. They're all running the same code, so that's what makes it an embarrassingly parallel problem. They don't need to coordinate anything. And they're all looking at different input, but they're doing the same processing. And they're all running in here. And these guys all run one time, one iteration. And when they're done, they decrement the barrier by 1, and that causes the main thread to continue on its way. Okay, any questions about that? And what we're searching for probably can't really see this, is we're searching for do, re, mi, fa, sol, la, ti, do. So we're looking for musical notes, and it's looking in these strings. I just had to come up with something that I could search on easily. OK, so that's basically CountDownLatch. Any questions about CountDownLatch? CountDownLatch is a very useful barrier synchronizer. Gets used all over the place. The problem with it, though, is it's only good for one-shot deals. You can only use it for one thing. Once you've counted down to 0, you can't reset it again. So it's no good for cyclic operations unless you want to go ahead and create a whole new CountDownLatch, which is expensive and may not work in some circumstances. So to solve this problem, Java has another barrier called a CyclicBarrier. And that's good for cyclic processing, and it's also good for await done barriers as well. One of the things it provides you, in addition to this cyclicness, is it also allows the count to be reset. So when you get to some number, you can turn it around and reset it to its initial value. So if it started out at n, where n was the number of parties, once you count down, you can say reset, and it goes back to n again. So this is useful for a fixed size number of threads that wait for each other to complete. This does not apply the bridge pattern. This is like completely unrelated to almost everything else in the Java synchronizer mechanisms. What you'll find is that the early stuff had a lot of commonality, and then as they got into more cool things, they're like, screw this commonality. We're just going to do something really custom. So it gets a lot less common over time as you get more powerful features. The constructor creates a new object that trips when a given number of parties are waiting on it. And it resets itself back to what it was before. So here's the way it works. You can give the number of parties, like n, where n is 4. And it also, optionally, can be given something called a barrier action. And the barrier action is really cool. It's a really clever idea. The barrier action is basically a hook method, the run method, because it's a runnable. It's a hook method that gets called by the last thread that enters the barrier while everybody is still frozen. So all the threads are suspended at this point. So when barrier action is run, when its run method is run, everybody else is waiting. They're not making progress. This is often used to do stuff that will cause things to be able to rerun some more. I'll show you how I use it in my ThreadGang framework in a second. OK, the key methods on a cyclic barrier, there's only a handful of them. There's await, 2 versions of await, and reset. So the first version of await, which is the blocking version, will just wait until all the threads arrive, the thread is interrupted, or the barrier is reset, which is called a broken barrier. Await returns the arrival index of the thread. So remember, we have threads there, 0, 1, 2, 3, 4, 5, 6, whatever. It'll tell you when await returns successfully, it'll give you back the number of the thread, the party, in the arrival order that was waiting. And you can use this to do stuff that doesn't require a barrier action. A barrier action is run when all the threads are suspended. So you want to keep that barrier action really short if you can. So sometimes you need it. Sometimes there are things you need to do while everybody else is frozen out. Other times, you need to just do something, and as long as one thread does it, you don't really care who does it, because they don't have to be synchronized. So here's an example where you have barrier await return 0, which means I'm the first thread, but it could be the nth thread, doesn't matter. And you're just going to go ahead and do something like log the completion of the iteration. But you don't have to have everybody else synchronized at that point. This await blocks until the timeout occurs or all the parties arrive. And then reset resets the barrier to the initial state, and parties are not suspended. That's a cut and paste error. Oh, I know what I wanted to say. I wanted to say something more interesting. I wanted to say broken barrier exception is thrown by await calls when barrier is reset. So that's how you know that things have been reset, because you get a broken barrier call. All right, that's what I wanted to say. Okay, so what we're going to do now in the remaining time, this should work out pretty well, is I'm going to show you an example of using a Java cyclic barrier. So if we go and look at our ThreadGang example, there's a search cyclic ThreadGang solution, which is part of the framework. And the way that this works is it's going to spawn off a thread for every element in the vector, just like we had done before. And actually, it's not going to use CountDownLatch. It's going to use CyclicBarrier. That's dumb. Sorry. That's what happens when you copy and paste stuff. So it basically will CyclicBarrier. So it's going to go ahead and use the CyclicBarrier to allow this thing to run as long as there's input. It'll keep running. The same threads will continue to process a new chunk of input each time. Now, the interesting thing about cyclic barriers, and this is really important to remember, much like CountDownLatches, you can't vary the number of waiters, parties as they call them. You can't vary them. They have to stay fixed. So if you start out with 8, you're going to have to keep 8. You can't start adding more. Even if you do reset, you can't add more. So that's a limitation with the cyclic barrier and the CountDownLatch. I'll show you some things that work around that shortly. Okay, so here then is the implementation we're going to look at. Here's a cyclic ThreadGang. So cyclic ThreadGang inherits a bunch of stuff from the common class. It uses a cyclic barrier. It uses a CountDownLatch to have the main thread be able to wait for the other threads to finish running the cycles. So it uses both barriers. Here's the constructor. It creates the CountDownLatch, so it can use that to wait till everybody else is done. Here's getNextInput. Now this getNextInput's a little bit more interesting than the one before, and that's because we actually have multiple arrays of input here. So if we go up here and we looked at fixed number, so fixed number of input strings have multiple arrays. The one-shot input strings just had one array. This one actually has multiple arrays. But they all have to have the same number of elements in them. Here's worker done. This is a little different. What worker done does is worker done waits for all the threads to reach the barrier. And once that's done, when they all hit await, then the barrier action, if any, when we have one, will be called with all the threads blocked. And then when the barrier action returns, await releases all the threads, resets the barrier so it goes back to the original number. You know, it starts with the initial number of parties. And then they can all loop back around again and start processing. So every time all the threads show up to await, the barrier action is called, if there is one, and then they get a chance to continue again with the next cycle, the next phase of processing. Any questions about that? So that's kind of like the wind sprints in the movie, right? When you're done, you go back and you all line up again. The coach blows the whistle. You all start skating or running. Jake.
And the other one was just did a countdown instead of a wait. Is that right?
So the other one, the only thing that was waiting in the other one was the main thread,
Right.
and the other guys were just counting down as they finished up their one shot. In this one, the waiting here is being done by every thread in the gang, and they're all waiting till they reach a common point, at which point new input is received.
The main thread's waiting too, right?
The wait thread is waiting too. Yeah, in fact, I'll show you that. The main thread is waiting on the CountDownLatch. So it's right here, await ThreadGang done. It just went in. John.
Is it possible for like one of the threads not to get past the awaken after the barrier action occurs? So imagine one of them like just doesn't make it while the barrier resets itself?
Sounds like a Hollywood movie, like No Man Left Behind or something like that. You know, the other threads have to go back and rescue the one that got blocked. No, no. That if that happens, it's the end of the world. I mean, bad things. It shouldn't be occurring. But somehow Chuck Norris is involved. You know, I guarantee you. So here's the interesting part of this. This is initiate ThreadGang. This does some interesting stuff. So notice what it does. When initiate ThreadGang gets called, it's going to go ahead and spawn all the threads, just like the other guy did. So this is going to spawn a pool of threads. But it does one other thing. It creates a new cyclic barrier with size elements in it. That's the count. That's the number of parties. And it also creates a barrier action. And here's what the barrier action does. The barrier action will get the next input. And if it succeeds in getting the next input, what that means is it's done, all the threads have processed the first round of input. They're all synchronized on a wait. Barrier action gets called. Barrier action says, is there any more input? If there is more input, then when the threads wake up, they'll say, aha, there's more input. Let's keep going. And they'll loop back around again, and they'll all start processing their new input that corresponds to their element in the vector. So until get next input returns false, this guy will keep running over and over again. It'll cycle through. That's why it's a cyclic gang as opposed to a one-shot gang. So the cool thing about all this, of course, is we're keeping exactly the same framework, and then we're just varying a few things. Here's run next cycle. Run next cycle is what gets called here. This is what controls everybody's loop. Each thread has a loop that it runs. Each worker thread has a loop. And the loop terminates when run next cycle returns false. And as you can see here, if there's more input, then we return true, because we can keep processing. If there's no more input, and the input was set by the barrier action, then we decrement the countdown latch to let the main thread go, and we return false, which shuts all our threads down. OK, so we've got like we've got 30 seconds left. I won't go over phasers. Phasers are the last thing we're going to do. If you really want to hurt yourself, though, take a look at the phaser implementation. Phasers are really cool, but wow, are they crazily insane. And so phasers, this phaser version, allows us to be able to add or remove the number of processing elements each cycle. And so I figured this out over the weekend, and I had way too much fun doing this. But this does all that stuff. It's really complicated, and it ends up using a cyclic barrier and a volatile flag and all kinds of other crazy things in order to implement the reconfiguration mechanisms. So we'll talk about phasers next time, and you'll get to see that.